Yesterday we did geometric vectors, so we were drawing these vectors out to kind of visualize what was going on. Today we're going to turn that into more of an algebraic way. It's probably going to be a lot faster to do things algebraically, but it's important that you understand visually, geometrically, what's going on before we jump into doing it algebraically. Let's start off and look at some vectors from yesterday. Now I'm going to give them to you a little bit differently. I'm going to put them on a coordinate plane rather than thinking unit circle with angle measurements and stuff. In this particular example, it says vector v is, and from geometry you might have spent one day doing vectors, maybe. But there's two ways to name vectors. You can use one letter, or you can call it like it's a directed line segment where it uses two endpoints. P is at -3, 1. There's P right there. And Q is at -1, 5, right here. So vector V is the vector that goes from P to Q. Then we have vector U, and it's the same idea. Let's plot R. It's at 3, -2, so there's R. And S is at 5, 2, right here. And vector U is the vector that connects those 2 points. So that's vector U. This one was vector V. Now it says, looking at the graph, how could we show that the two vectors are equal? Meaning, okay, so for vectors to be equal, remember they have two properties. They have direction and they have magnitude. Looking at my two vectors, do they look like they're going in the same direction? Well, yeah, they're kind of going up and over about the same amount, okay? And their magnitude is their length. Do they appear to have the same length? Yeah, they kind of appear to. But how could we prove that? What are the things that we would do to show that those are the same? By placing these vectors on a coordinate grid, it should lead you to some formulas that you should know to show that these are going the same direction. I kind of hinted at a kind of going up and over the same amount. Well, that's slope. If you can show that they have the same slope, that's going to force them to go in the same direction. So you're going to prove they have the same slope. Now, typically what we're doing is if we're trying to show that the vectors are equal, then we have to show that process of finding slope. We just can't say, blah, they're the same, whatever. We typically, now, actually I do get to kind of say they're the same because I took the time to graph them. So I can count the rise, 1, 2, 3, 4, and the run, 2. 4 over 2. That's a slope of 2. So the slope on vector V is equal to 4 over 2 or just 2. And I can do the same thing. I can say that the slope of vector U is also rise 4, run 2 is going to be 2. If we didn't take the time to graph them, which many times, well, probably a lot of time, we're not going to have graph paper to do that. We're just going to do the slope formula with our two ordered pairs. So you might end up finding yourself doing the slope formula. Okay, the second part, the magnitude. How do I find that they are the same length? Well, if I've got them plotted on a coordinate grid, or really if I just have the ordered pairs to find their length, I'm going to do distance formula. I have to show that they have the same distance between their 2 points. That one, whether I have it graphed or don't have it graphed, I'm going to have to show that. Let's try that. I did not leave myself very much space. That wasn't very smart, but here we go. I'm going to find the distance between these 2 points. You need to know your distance formula. Distance equals big square root. I got x minus x. I'm going to go with -1 minus -3 squared plus, and then do y minus y. 5 minus 1 squared. Change that. That's going to be 2 squared, so that's 4 plus, that's 5 minus 1, that's 4 squared plus 16, that's the square root of 20. And I could reduce that if I want, But then I have to do the same thing with this one. I'm going to come down here where I have some more space. So the distance between those 2 points, big square root, x minus x, 5 minus 3 squared, plus y minus y, 2 minus negative 2 squared, change. All right, it looks like I end up with the square root of, that's 2 squared, that's 4, plus, that's 4 squared, 16. Hey, that looks familiar. That's going to be the square root of 20. And I've managed to show then that their distances are the same, which makes their length the same, makes their magnitude the same. On your homework then, they're going to ask you to show that the vectors are equal. It probably implies they are going to be equal, but you have to show it by doing the slope formula and doing the distance formula and showing me that you get the same thing. If you get something different, then that's going to tell you that they are not equal vectors. Now, that's a little bit time consuming to go through all that work to show that they are equal. We actually have a nice way to tweak those vectors to show that more easily, and that is to put them in standard position. Standard position means that you're going to take their initial point, wherever it is, and you put it at the origin. If you were to take both of those vectors and shift them so that they were in standard position, they would have brought down that initial point right here, and then that slope would have still been rise 4, run 2, still would have been here, but they would have landed on top of each other right here, and it would have looked like this. And if the two vectors land on top of each other, then they're going to be equal. All right, so we got that. How do you just move those two vectors, though, so that they do look like that and are in standard position? Well, some of it just takes a little bit of common sense of just shifting them and that translation that happens. But once you get them in that position, how are you going to tell that they're the same thing? Well, it's how we name that vector now. Instead of just calling it vector u or vector v, we notate what this endpoint is right here. Or I say the endpoint, it's the terminal point. So right here, if we place these vectors in standard positions, then we can represent them in what we call component form. The component form simply shows what that terminal point is where they end up. What do you think this terminal point would be on that vector from the previous example? Well, we said we went up 4 and over 2. So that ordered pair, I'm looking for that ordered pair, would be 2, 4. But since it's a vector, and it's more than just showing that ordered pair, we're showing it as a vector, we have different notation. To show this vector in component form, instead of using parentheses, we use these pointy bracket things. And so vector v or vector u, either one, once you put it into standard position, would look like this. And the x term is what we call our horizontal component. It tells us how much we're going to move horizontally from our initial point. And the second number is your vertical component. It tells you how much you're going to move up or down from your initial point. This vector, rather than writing with all those ordered pairs, is really just written like this, and that's called component form. And that's what we're going to use most of the time. Let's take one of these then that wasn't, and this is vector v from previously, it didn't give it to us in vector form, or I'm sorry, in component form. And I don't really want to take the time to graph every single one of these. Let's look at how you can just convert that to a component form. You're basically looking at what changed on your x's. If you look at the difference of your x's, so I started here and ended here, so take x2 minus x1, -1 minus -3, and we get a positive 2 out of that. And then do the same thing with the y's. Take your end point, subtract your initial point, so 5 minus 1 gets me the vertical component. And that's what we'll do rather than having to graph all of those. Remember, we're starting to look at things more algebraically, trying to pull away from having to draw everything out. But the understanding of the drawing is important so you can visualize what's going on. All right, the next part is finding the magnitude of that vector. Well, the magnitude is its length, and we could do distance formula, but remember we're going to change this and we're going to just be writing this in component form now. Well, it really, if you think about it, if I have this and I have it drawn up here, to find the length of that, it's really just a little Pythagorean theorem step. If you form that little right triangle, it's x squared plus y squared, and then you square root it, and that's going to get you your hypotenuse. Or you can think of it also as the distance formula, but one of the endpoints is 0, 0, so that makes your distance formula work real slick. Anyhow, this is then the formula. You're going to take one of the components and square it, plus the other component and square it, and then take the square root. A is going to be your horizontal component, B is your vertical component. This right here is the notation for the magnitude. When you put these bars around your vector, you're not talking about the actual vector anymore. You're talking about what its length is, what its magnitude is. The magnitude of this one, basically if it's in component form right here, I'm going to take 2 squared plus 4 squared. That's 4 plus 16. The square root of 20. Does that look familiar? Isn't that what we had? But isn't this way faster than having to work through the distance formula? It works nice if it's already in component form for you. I went ahead and took that to the next step and reduced that. Okay, this is important. Star this. This is how you find the magnitude of a vector. Now, before we get too far, let's kind of tie this all back together and kind of start from scratch and see if we can do this. I'm going to take this directed line segment, or this vector, where it's given to you with 2 ordered pairs rather than giving it to you in component form. So what I'm going to do is I'm going to convert it to component form first so that I can quickly find the magnitude of it. All right, so to convert it, remember I'm looking for, if I were to take these and shift it, I'm not going to draw it out. Basically, if I were to shift this and put the initial point at the origin, I'm really looking at what happens with my x's and what happens with my y's. So I'm going to take x2 and subtract x1. And this is going to be my component form, so I'll use the little pointy bracket now. It's going to be 2 minus negative 5. And then I'm going to do 6 minus 3. The order that you do that subtraction is very, very important. You have to do the end point minus the initial point. Otherwise, you're going to end up in a different quadrant. This component form of a vector is 7, 3. That's where this would end up if I had moved it. Let's sketch it just for the sake of sketching it so you can visualize it. My starting point was negative 5, 3, and then 2, 6, something like this. It was this vector right here, but then I'm going to grab that vector and I'm going to move it so that this initial point is really here. And it would look something like this then. So does this point 7, 3 make sense then for an end point or a terminal point? It should. All right. The other part that we're supposed to do is find the magnitude. Remember the quick, easy way to find the magnitude. Now this is vector P, so I'm going to use some nice notation here, put bars around it. I'm looking for the magnitude of vector P. Probably up here I should have said just vector P equals. It doesn't have the bars. Now I'm doing the magnitude of it, and that's just the square root of a squared, so that's 49, plus b squared, that's 9, and 49 plus 9 is the square root of 58. The square root of 58 is not going to reduce for us, so there's your magnitude. All right, so that's about all we've learned so far, is just understanding what component form is and how we can then go to the magnitude of that component form. Now we're going to move on and we're going to look at those geometric vectors that we did yesterday. Do you remember how we would add two vectors together? Maybe we'd subtract or multiply by 3 or something. All right, we're going to do that same thing, but we're going to look to do it maybe a little more quickly. It's not quite the same thing that we did yesterday. Not yet. We're going to get there. But I'm going to give you two vectors in component form. Now this isn't, I didn't give them to you in component form. Remember yesterday they were like at a degree measurement and told you how long, told you the direction and the magnitude. I'm just giving you the component form. Could you add these two vectors together? Well, here's my 2, 5 vector. Here's vector v. And then vector u, if I did the tip to tail thing, I'd have to go left 7 and up 2, so there would be the next vector right there. And what I'm looking for is this resultant vector right here. Well, if I graph it on a coordinate plane, you can see what this terminal point is right here. I'm guessing that I'm supposed to end up with a -5 and 7. But I'm looking to not have to graph it. Could I come up with that from these component form vectors and not have to mess with this? Could we do it algebraically? Yeah, we could. All you have to do is add the component forms. If you look at this, if you take and add the horizontal parts, I'm just taking 2 plus the -7, and then add the vertical components, 5 plus 2, and look at where you end up. -5, 7. I got the same thing. I don't have to graph it all. All I'm doing is adding the two vectors together. Easy peasy. So let's try it again. I'm going to show you what's going on, but there's no sense in really drawing this out. This time on my same two vectors, I want to do 2 times vector v. That means do vector v and then do vector v again. And you might be able to figure out what this terminal point is, but I'm going to look at it algebraically. I want to take 2 times vector v. That means 2 times both components. 2 times 2 is 4. And 2 times 5 is 10. And that is 2 times vector v. Does that look like what this point right here would probably be? Yep. Not even going to mess with graphing this one. Let's just try again. A little bit fancier. Would probably be smart to take a few steps of work. I'm going to take vector u and I'm going to subtract 3 times vector v. So I'm going to write this out. I've got to take my vector u, that's -7, 2. And I'm going to subtract 3 times vector v. Alright, first thing I'm going to do is go ahead and get rid of that 3. Let's go ahead and distribute that into the vector. That's going to turn that into a 6, 15 vector. And once I've got it down to 2 component forms, I'll go ahead and just do the subtraction. -7 minus 6 is -13. 2 minus 15 happens to also be -13. There's my resultant right there. Now, doing the algebra when they're already in component form is super easy, but really what you were doing yesterday on the geometric vectors, those weren't in component form. They looked something like this. I told you a direction via a degree measurement, and I told you a magnitude. What we have to do now is we have to take this information and turn it into component form. Remember, component form boils down to figuring out this ordered pair right here. How do you think we could find that ordered pair right there? And I'll give you a hint. Let's draw a triangle. Do you think you could figure out that ordered pair? I hope you're thinking SOHCAHTOA. For the component form, I need to know the horizontal component first. Well, let's see. I've got the hypotenuse, and from the 33 degrees, this is the adjacent. Looks like I need to be doing cosine. To find the horizontal component, I'm going to take the cosine of 33 and set it equal to, I'll call it x over 12. Multiplies both sides times 12. I'm going to my calculator here. Make sure you're in degree mode. And you go cosine 33 and multiply it by 12. It looks like my x value, or my horizontal component, is 10.06. Now let's do it again, but this time I need to find the vertical component. Still using my 33 and my 12, but this time I need the opposite. Looks like a sine problem. The sine of 33 is equal to the opposite, which I'll call y, over the hypotenuse. Sine of 33 times 12 gets me a y value of 6.54. Ultimately, though, how I want to write this is I want to write it as a vector in component form. There's your horizontal component. Here's your vertical component. And now, if I wanted to start doing the algebra on that, I could. Now, we're not going that far today. We've done about half of this lesson, this 6.1, and we're going to call it quits now. But just so that you get familiar with that component form and all the different things that you can do with that before we move on for tomorrow's lesson. All right, good luck.